Okay, I hope that you started by going to the intro video and watching the demo that was from online. In section 7.1, we're going to use what we just saw in that demonstration to tackle something called the central limit theorem. The central limit theorem is key to what we do for the rest of the time. It is one of those big ideas. So, here's the central limit theorem. There's a lot of parts here that we need to kind of go through. So the central limit theorem, and we're just going to call it the CLT. So when you see the CLT here in a minute, that's what that means. It means if I have a population, the mean is mu, the standard deviation is sigma. So any population, okay, the sampling distribution of the sample means has these three characteristics. Do you remember that on that demonstration, that no matter what it started with, remember that last one was kind of wacky? No matter what it started with, when it grabbed some random pieces of data out of there, and it went down here and started graphing those pieces of data, and it found the mean of these five, or the standard deviation. We did that too. When we did the mean of the sample, and then we took all of these and we found the mean of both of that, this is the sampling distribution of the sample means. Okay, so what happened was that the mean of the sampling distribution, which we're going to call x bar, so this is mu sub x bar, mu sub x bar, the mean of the sampling distribution of the sample means equals the mean of the population. So in English, that means when we took the sample mean, we took this sample and we found the means, the mean of the samples was the same as the mean for the population. So this is the mean of the population, and this is the mean of the sample means. And again, that's called mu sub x bar. Alright, second thing that happened was we noticed the standard deviation wasn't equal. So what happens is the standard deviation of, this thing did not move to where it's supposed to be, so I'll just redraw it here in a second. I'll rewrite it. The standard deviation of a sampling distribution of sample means is found using, this is standard deviation, so it's sigma. This is sigma sub x bar equals sigma over square root of n. This is the formula. So this time when I take my sample and I find its standard deviations when they drop down here, and then I take all my standard deviations of all the samples, I get a new standard deviation that is the old one divided by square root of n. Remember how it wasn't the same. It was much smaller. That's because we're going to take the standard deviation and divide it by the square root of n. Okay? And then that's going to give us the standard deviation of the sample distribution. Alright, number 3, the third part of the theorem says that the shape of the sampling distribution of sample means approaches that of a normal distribution, regardless of the shape of the population distribution. The larger the sample size, the closer to normal it will be. And we like n greater than or equal to 30. So let's go back to that demonstration that I showed you. When we started doing this, and we did a bunch of them, and we got all kinds of different means going on in here, and then it ended up looking normal. no matter what this started with, the mean of the sample means looked normal when we got done. Okay? And so this distribution, the mean of the sample means, that distribution looks like a normal distribution. And it behaves that way, especially when the sample size is 30 or more. So remember, I was doing sample sizes of 5 to start with to show you where these came from. And then I did samples of 10,000. 10,000 made it go way to normal really fast. I wish they had an in-between, but they don't. But there you go. Okay, so when I say central limit theorem, when we say CLT, what that means is I've got some kind of weird population up here, and it doesn't matter what it is. But when I take the mean of the samples, and I take the mean of their sample means, that the mean is the same, and the standard deviation of the new is the old standard deviation divided by square root of n. And it looks like a normal distribution when the sample size is at least 30. We like samples of at least 30. Okay? Just kind of a key number in there that just kind of hits the right spot. All right. So when I say the central limit theorem, this is what's happening. Whew. That's a lot to absorb. All right. So we're going to just kind of look at this with, I was thinking there's something else. We're going to look at this with just some numbers, and then we're going to throw words into it in the next video, okay? So this says the mean and standard deviation of the sampling distribution of sample means is what we're going to find. So what the heck is that? That's mu sub x bar and sigma sub x bar. That's what they want you to find. Find the mean of the sample distribution of sample means. Another way to say this, and the way that I usually say it, is the mean of the sample means. Okay? And the standard deviation of the sample means. X bar, sample mean, remember? All right, here we go. The mean of the sample means is equal to, well, it's equal to mu, remember? So that is 12. Yay. Done. Sigma sub x bar is equal to sigma over square root of n. That was our formula of the day. So I'm going to take 2.3 divided by the square root of 36. So let's divide. 2.3 divided by 6 is 0.38. 3 repeating. We'll just tack a 3 on there, okay? So nothing horrible. This is pretty. That's all it wanted you to do. Find the mean of the sample distribution and the standard deviation of it, okay? And it doesn't matter what our original one looked like. All right, I'm going to show you some examples in the next one.